Today we're going to continue our discussion about hypothesis testing with a little bit of a talk about testing a claim about a mean. Now, they claim that this is one of the most important methods that's in this book. I don't know that I would say most important, but certainly one of the most commonly applied things. So as you're going out and you're noticing statistics in the wild, this is something you are likely to see at some point. So part one, and really the majority of this video, is going to be dedicated to times when we don't know the population standard deviation. And then at the very end, we'll talk about what can we do in those rare instances when we actually do know the population standard deviation. Our objective is going to be to use a formal hypothesis test to test a claim about a population mean. Our notation hasn't changed. N is going to be our sample size, X bar is our sample mean, S is our sample standard deviation, and mu is our population mean. You'll notice that we have mu sub X bar here. Remember, this is the mean of our sampling distribution of means, which is an unbiased estimator of our population mean. The requirements that we need to be able to test a claim about a population mean when we don't know our population standard deviation are that our sample is a simple random sample, and the second one hopefully reminds you a lot of the central limit theorem, because it's basically that our population is normally distributed, or our sample size is greater than 30, or both. If we're going to test a claim about a mean, then we need to test statistics. So that's going to be T for us when we don't know our population standard deviation. So T is going to be found by taking our sample mean minus our population mean and dividing that by the quantity of our sample standard deviation divided by the square root of our sample size. When we're looking to use p-values, we can use technology, or we can use table A3, our student t-distribution, with degrees of freedom given by 1 less than our sample size. Now, if we're using critical values, we're going to use the student t-distribution, table A3, and again, our degrees of freedom of 1 less than our sample size. Right, so again, we have this requirement of normality, or n is greater than 30. This is our central limit theorem type of stuff. And basically what we're saying here, if our original population is not normally distributed, then we use n is greater than 30 to justify using the normal distribution. If it's not greater than 30, we're going to say it's a no-go. But know when you're encountering stats in the wild, sometimes when sample sizes are between 15 and 30, and they say that that's enough if the population is close enough to normal. So to get out of that gray area and to avoid that gray area as we're just getting introduced to this, we're going to stick to n's got to be greater than 30. If it's not, you get to say, can't do it. All right. So, student t-distribution also hasn't changed since we first looked at it with confidence intervals. It is different for different sample sizes, and it has that same general bell shape of normal distribution, but it's a little bit wider, a little bit shorter, and the standard deviation associated it was larger. All right, so the mean 0, standard deviation is going to be greater than 1, and as our sample size gets larger and larger, our degrees of freedom increase. The student t-distribution gets closer and closer to our standard normal distribution. So let's look at an example. Adult sleep. Right. So the author obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study, and those times and hours are listed below. Here are the unrounded statistics for this sample. Right. So they give us a sample size of 12. They give us a sample mean of 6.833333. That value came from taking the mean of those 12 numbers listed at the bottom of this slide. And we have a sample standard deviation of 1.99240984. You could also calculate that using the 12 numbers at the bottom of this slide. If you want some practice calculating sample means and standard deviations, go for it. This would be a great thing to do with this. So, a common recommendation is that adults should sleep between 7 hours and 9 hours each night. Use the p-value mentioned with a 0.05 significance level to test the claim that the amount of sleep for adults is less than 7 hours. So, our requirement check. Sample is definitely a simple random sample. Our second requirement is that the population is normally distributed or n is greater than 30. Well, the sample size is 12, which is definitely not greater than 30. It doesn't even fall into that gray area if we were using that. So we must determine whether the sample data appear to be from a normally distributed population. So we do our best with that by building a histogram. So we take a look at our histogram and we say, that looks pretty normal. All right. They've also constructed a normal quantile plot there, and we can see that it looks pretty linear. And so we have that this is approximately normal, and we can proceed. So step 1 in our hypothesis testing. We're going to look at the claim that they made. So the claim is the mean amount of adult sleep is less than 7 hours. So if we use symbols to represent that, that's saying that mu is less than 7 hours. So step 2, we identify what the opposite of that claim is. Well, the opposite of less than is greater than or equal to. So the opposite of that is that the mean is greater than or equal to 7 hours. Now we have to decide what our null and alternative hypotheses are. So we take a look at the two symbolized claims that we have above, and we find the equal sign. It happens to be in the one in step 2. We pull that equal sign out, and we make that our null hypothesis. So our null hypothesis is that the mean is equal to 7 hours. Then our alternative hypothesis is the claim from step 1 and step 2 that doesn't have the equal sign. So that would be that the population mean is less than 7 hours. That's also the original claim that we were wanting to test. So it's perfect. All right, we have our null hypothesis, we have our alternative hypothesis, ready for step 4. The problem statement told us that it wants us to test this at a significance level of 0.05. So that's identified for us. Step 5. Because the claim is made about the population mean and the sample statistic most relevant to this test is the sample mean, then we're going to use the t-distribution. All right. This is also because we don't know the population standard deviation. So we're ready to move into step 6, our solution. So the sample statistics of n equals 12, x bar equals 6.83333333, and s equals 1.992400984 are used to calculate the test statistics. So we plug them in and churn out a t-value of negative 0.290. Right. When we're doing this calculation, and the reason we were given all of these sample statistics unrounded is it's best to carry as many decimal places as you can and avoid rounding so that we get the most accurate value for t that we can. So now, looking at the solution, we could use technology, except again, we're not using technology. We want to be able to read the displays of technology, but that's what we're looking for. So our technology will give us a p-value of 0.38868888459. You can read various versions of that on all of these different types of technology here. When we round it, it's 0.3887. All right. Again, you don't have to be able to actually plug it in and do this with any of this technology, but you do need to be able to read the screens and know what it's telling you. All right, so once we have our p-value, then we know that 0.3887 is greater than our significance level of 0.05, so we fail to reject the null hypothesis. And in our interpretation, we say, because we fail to reject the null hypothesis, we conclude that there is not sufficient evidence to support the claim that the mean amount of adult sleep is less than 7 hours. The situation that we're going to be in is, instead of using technology, we'll be using table A3 to identify a range of values containing the p-value. So in using table A3, we're going to keep in mind that it's designed for positive t-values and right tail areas only, but it's awesome. The probabilities that it gives us work for us for a left tail thing if we just change values of our t-values to be negatives. That's because it's symmetric about 0. All right, so we have our t-value of negative 2.90 and a sample size of 12. So our degrees of freedom is going to be 12 minus 1, which is 11. So now what we're going to do is we're going to go to table A3. We're going to go look at the row for degrees of freedom 11, and we're going to search it for the positive version of our t-value that we calculated. So we'll be searching for 0.290 in the row that's the degrees of freedom 11 row. Well, that value happens to be less than all of the listed t-values in the row. So that indicates to us that the probability is in fact greater than any of the probabilities on that page, which tells us that the probability is greater than 0.1. All right, and that's all the right tail thing, but again, it's symmetric at 0, so putting it as t is negative 0.29, we're looking still that our probability is greater than 0.1, that we get a t statistic less than that. So in this case, table A3 is allowing us to conclude that the p-value is greater than 0.1. Technology gave us an exact p-value of 0.3887, but ultimately we come to the same conclusion because we have that threshold, our level of significance is 0.05, and regardless of whether we know exactly what the p-value is or not, we can make the same conclusion. Right. So again, this was our left-tailed test with our t distribution. Take a look at that table. Make sure you understand what's going on there. All right. Now, if we instead used critical values instead of our p-value method, what we would do is we would say, hey, significance level of 0.05. So we would say, all right, 11 degrees of freedom. We go to that row. We go to the 0.05 column, and that gives us a t-value of 1.796, all right? But remember, that's telling us that that's the t-value for the right tail test. So we need the left tail test, all right? And to make a right tail test into a left tail test, you just add a negative sign. Again, make sure that you're identifying the columns based on the area in one tail instead of the area in two tail labels, because we're dealing with a one-tail test here. All right, so we have a critical value of t is negative 1.796. So here we have our test statistic was negative 0.29. Our critical value is negative 1.796. So we draw a little picture here. We identify our critical value. We identify where our test statistic is. And we've shaded in our critical region green there to the left of our critical value. Notice our test statistic falls outside of that because it is greater than negative 1.796, and we're doing a left-tailed test. So our conclusion is again the same that we would have made in our p-value. We would fail to reject. All right, so another alternative is that we use a confidence interval method. Right? So a one-tail test was what we were dealing with. We want to look at 0.05 being the area in the left tail. And remember, confidence intervals have both a left and right tail by nature. We can't change that. So we're looking at 0.05 plus 0.05 because our confidence interval is going to be symmetric at our mean. So we're looking at 10.1 in our tails, or 10%, which means 90% is going to be in our confidence interval. So we're constructing a 90% confidence interval. If we go through the steps to do that, then we'll get an estimate of the population mean being between 5.8 hours and 7.87 hours. Well, 7 falls within our confidence interval, and that means that it could be that the population mean really is 7. All right, so we don't have sufficient evidence from our confidence interval method to reject our null hypothesis. So we fail to reject the null hypothesis, and we get the same conclusions that we did in our p-value method and our critical value method. All right, another example. Is the mean body temperature really 98.6 degrees? This is different than the other examples we've done so far because this one doesn't talk about things being less or greater than. So it's just saying, is it really actually this? All right. So we have a data set of body temperatures, and it has a sample size of 106, a sample mean of 98.2, sample standard deviation of 0.62, and we want to use a 0.05 significance level to test the common belief that the population mean is 98.6 degrees. So, requirement check. The study design used, it can be treated as a simple random sample. And so then we have to check the population normally distributed, or n greater than 30. In this case, the sample size is 106, so we don't have to worry about whether it looks normal or not. All right, so step 1. The claim that the population mean is 98.6 degrees. Well, that's that the population mean equals 98.6 degrees. That's our symbolic form. The opposite of equals to is not equal to. All right, so here we go through and we say, what's our null hypothesis? Well, it's the one with the equal to sign. So our null hypothesis will be that population mean equals 98.6, and our alternative hypothesis will be the one without the equal sign, which is that the population mean is not equal to 98.6. So step 4, they gave us that the significance level is to be 0.05. And again, population mean is what we're looking for, so sample statistic is going to be our sample mean, and we don't know our population standard deviation, so we'll be using a t-distribution. So we calculate our t-statistic. We plug in our 2 means and our sample standard deviation, our sample size, and we get a t-value, a test statistic of negative 6.64. There's a little bit of a typo on that, but not a big deal. All right, so go through, calculate t. Great. So now we have options on how we go about this. Using the p-value method, right? If we look for that t-value that we found, or the positive version of it, as the case would be, we end up finding that this falls into the category of p-value is 0.000, or basically 0. All right, it's less than 0.01 if we use our table A3 when we're looking for stuff. All right, it falls into that band. If we use critical values, the critical values are going to be plus or minus 1.983, or plus or minus 1.984 if we're using the table. Right. And if we use a confidence interval, this time we're doing a two-tailed test, and we want 5% in the two tails combined, so we are looking at a 95% confidence interval. And if we calculate that, we get 98.08 degrees up to 98.32 degrees. So our solution, all 3 of our approaches lead to the same conclusion. The p-value is less than the significance level of 0.05, so we can conclude that it is in fact significantly weird. The critical values, our test statistic of negative 6.64 falls into the critical region. That is the values outside of plus or minus 1.983. And with our confidence interval, 98.6 does not fall within our confidence interval. So, with all three of these, our conclusion is that we reject our null hypothesis. So, there is sufficient evidence to warrant rejection of the common belief that the population mean is 98.6 degrees. And I just want to let you know that if the population is not normal and the sample size is less than or equal to 30, there are options out there. There's this idea of bootstrapping, there's a sign test, there's the Wilcoxon signs ranks test. All of those things are outside and beyond the scope of our course to talk about, so don't worry about them, but I want you to know that they exist. And now finally, as promised, what happens when we know the population standard deviation? Well, everything works the same, except we can use the normal distribution. So we can use the Z statistic. So Z is going to equal our samples mean minus our population mean divided by the quantity of our population standard deviation divided by the square root of our sample size. Everything works the same except for we'll use the standard normal distribution, table A2, instead of our student t distribution, which was table A3. That's all. That's the only difference.